Hi everyone, this is teacher Lou from Delta Learning Space, and today we are going to speak about the types of real numbers, and this is part of our number property series. And before we get started, there is a guided notes PDF available in the link in the description, and this is just a note page to help you follow along with everything that will be discussed in this video. And so when we talk about numbers, there's two big categories. There are real numbers and there are imaginary numbers. Today, though, we will only be speaking about real numbers, and then in a future video, we will talk about imaginary numbers as well. So the set of real numbers encompasses so much, and so here we are just being presented with 5 subsets of those real numbers. The first subset that we have are called our counting numbers, and so these will be our whole numbers that start from 1 and go until infinity. These are also known as our natural numbers. Counting numbers, just as the name suggests, are the numbers that we use to count. We start with 1, then 2, 3, 4, 5, and then we can continue until infinity. Our whole numbers will be our counting numbers with the addition of 0. So above we had 1, 2, 3, 4, 5. But now for whole numbers, we will also include 0. Our integers will be our whole numbers and their negative or opposite values. So let's see what that looks like. First, I'm going to include our whole numbers, 0, 1, 2, 3, 4, and 5. And their negative or opposite values will be to the left of the 0. While we have 1 to the right of the 0, we will have negative 1 to the left. Negative 2, negative 3, negative 4, and negative 5. And while we can continue in that positive side until infinity, we can also continue in that negative side until negative infinity. So I'm just going to put ... For our fourth and fifth subset of real numbers, our rational numbers and our irrational numbers, we'll take a closer look at in just a bit, but for right now, we'll give the brief definition and then a few examples. So for our rational numbers, these will be numbers that can be written as a ratio. These will include terminating and repeating decimals. And so we will have some integer p over some integer q. The only restriction is that q will not be equal to 0. And so just to give a few examples, our integers, whole numbers, and counting numbers are all examples of that. I'll just put a few. 1, 2, 0, and negative 3. Anything that's a ratio, and that will be fractions, I'll put 1/4. Terminating decimals, I'll put 0.25, and a repeating decimal, so we'll put 0.3 repeated. All of these will be examples of rational numbers. On the irrational side of things, these will be numbers that cannot be written as a ratio. These will be decimals that do not terminate and do not repeat. Here we'll just give a few examples. Our first example will be the math constant pi, and we will estimate that at 3.14159. Our second example will be the math constant e. This is called Euler's number, and we can estimate that to be 2.71828. And our third example will be the square root of 2. The square root of non-perfect squares will be considered irrational, and this will estimate to be 1.4142. All three of these examples will not terminate and not repeat, and those are some of the defining features of irrational values. And so while our counting, whole, and integer numbers may be values that we're a little bit more comfortable with, let's take a closer look at rational and irrational numbers. So rational numbers are numbers that can be written as a ratio. These will include our terminating and repeating decimals. But what does that mean? So we will have some integer p over integer q. And here is just our ratio. The biggest restriction with our ratio is that our denominator cannot equal 0. Our integer p could equal 0, but our integer q cannot. So here I just pasted the examples from the previous page. Let's take a look at the first three examples. 1, 2, and 0. These are whole numbers, these are integers, but they don't exactly look like a ratio. Every whole number can be rewritten as a ratio. 1, 2, and 0 will be in the numerator, and when we want to represent a whole number as a ratio, we simply put it over the value 1. 1 over 1 will simplify to 1, 2 over 1 will simplify to 2, and 0 over 1 will simplify to 0. We can also represent these in different ways. For example, to represent 2, 4/2 is equivalent to 2, but these are just reasons for why these are considered rational numbers, different representations of the same value. And so our fourth example, -3. -3 is an integer, and I can put it over the integer 1, and that will simplify to -3. Our fifth example, 1/4, is already written in ratio form, and so we don't have to do any additional things to make it look like our integer p over integer q representation. Our decimal, so here we have a terminating decimal. It ends at 0.25, and every terminating decimal can be rewritten as a fraction. 0.25 can be rewritten as 25 over 100. And our last one, that 0.3 repeated, every repeating decimal can be represented as a ratio. 0.3 repeated is equivalent to 1/3. And that is why in our definition, we include terminating and repeating decimals, because both of these values can be represented in ratio form. Anything that can be represented in a ratio form, like how we see here, is considered rational. Now let's take a look at our irrational numbers. These are numbers that cannot be written as a ratio. These will be decimals that do not terminate and do not repeat. And here I've pasted the three examples from the previous page: pi, e, and the square root of 2. And all of these values will never end, and there will be no repetition. E, it will look like there's a repetition, but as you go further into the value system, like as you go further into that decimal, you will find that it's not a true repetition. All of these numbers here, and while you may see these as estimated ratios, they will not be exact values as ratios. If we input any of these values into a calculator, we will see that it ends, but it's only ending because of the capabilities of the calculator. These numbers will continue until infinity, and that is what is going to constitute them as irrational numbers. Irrational numbers, though, are all still real numbers. Okay, so I know that may have looked like a lot, but now let's take a look at this in a graphic form. Our white space is representing our real numbers. Everything here is considered to be a real number. The first subset we are going to look at, though, will be our counting numbers, represented in orange and is the smallest. The examples of our counting numbers that we had are 1, 2, 3, 4, and 5. Counting numbers will fall under whole numbers, so everything that is a counting number will also be a whole number. So I'm just going to repeat 1, 2, 3, 4, and 5. The difference between whole numbers and counting numbers is that whole numbers will include 0. Now let's take a look at our integer numbers. integer numbers will include our whole numbers, will include our counting numbers. So I'm just going to rewrite that. 0, 1, 2, 3, 4, and 5. But now also including those negative values. -1, -2, -3, and I ran out of space, but that's going to continue in the negative direction. And lastly, our rational numbers will include our integers, will include our whole numbers, will include our counting numbers. So we kind of have this nesting pattern going on. So I'm going to rewrite everything that was found in our integers. Well, I'm only going to write a few because I'm going to run out of space. Rational numbers, though, will also include everything that can be represented as a ratio. I could write 1/2. Terminating decimals can be rewritten as a ratio, so I'll write 0.25. Repeating decimals can be rewritten as a ratio, so I'll include 0.3 repeated. And here we just have a few examples of irrational numbers. And while still a real number, but not included in our nesting pattern that we saw with our rational numbers, integers, whole, and counting, we have our irrational numbers. And we saw the 3 examples there at pi, square root of 2, and Euler's number. And these are just 3 examples of irrational numbers. So while we saw that the square root of 2 will be irrational, now let's take a look at perfect squares and what is going to make a square root rational compared to irrational. And so square root is an operation that for the value underneath the square root, we are looking for 2 numbers that are the same, that when we multiply them will equal the value underneath the square root. I think this, though, is more easily seen in a graphic form. So here I am just going to make a perfect square. Here I have 1 perfect square, and the length of that is 1 unit by 1 unit. So 1 times 1 will equal 1. I can expand that to a 2 by 2 grid. And so in this 2 by 2 grid, it is 2 units by 2 units to get us 4 square units. And so now let's just find our perfect squares from 1 to 100. Like we saw above, 1 times 1 equals 1. The square root of 1 is 1. 2 times 2 equals 4. The square root of 4 is 2. 3 times 3 will equal 9. The square root of 9 is 3. And so because we have these whole numbers that these square roots can simplify to be, these values will be considered rational. So now take a moment and finish up until the square root of 100. Amazing. So now we have our square root values that will simplify to a rational number. Any square root value in between will be considered the square root of a non-perfect square, and those will be considered irrational. Between the square root of 1 and 4, we have the square root of 2 and the square root of 3, and these will be irrational. Between 4 and 9, we have the square root of 5, 6, 7, and 8, and those will also be considered the square root of non-perfect squares and irrational. Now let's do some guided practice. On your notes page, circle all of the whole numbers, square all the integer numbers, and underline the rational numbers. And note that a number may get more than one symbol. Now let's take a look at our answers. First, we will circle all of the whole numbers. 5, 0. If it asked for counting numbers, that 0 would not have been included. 2, 1,500, And because the square root of 16 can simplify to 4, this will be considered a whole number. Next, we will square all the integer numbers. Everything that has a circle should also have a square. Every whole number is also an integer. And our negative whole numbers are considered integers, so negative 11 will also get a square. Lastly, we will underline the rational numbers. Again, because we had this nesting pattern, anything that already has a symbol should now also get an underline. Anything that can be represented as a ratio or a fraction is rational. Terminating decimals are rational. And repeating decimals are rational. The only number that we have that will not get any symbol is our value pi, because that is irrational. So I'm just going to X that out. Now let's take a look at some other number classifications. The first two that we have are even and odd numbers. So even numbers will be numbers that can evenly be divided by 2, meaning you will get a whole number answer. These numbers will always end in 0, 2, 4, 6, or 8. A few examples of that will be the number 0, 24, 5,372, and 18. All of these will be considered even because their last number either ends in a 0, 2, 4, 6, or 8. Odd numbers, on the other hand, are values that cannot be evenly divided by 2. These will end in 1, 3, 5, 7, or 9. A few examples of that are 1, 17, 2,469, and 85. Because these values either end in 1, 3, 5, 7, or 9, they will be considered odd. Even and odd numbers can be both positive or negative. I can make this negative 24, negative 18, negative 1, and negative 2,469. The next number classification that we have are prime numbers. And prime numbers will only be considered for natural numbers. And these will be numbers that have only 2 factors, itself and 1. The number 1 will not be considered prime because it only has 1 factor, itself. Our smallest prime number will be 2 because it can be evenly divided by 2 and 1. Any even number that is larger than 2 will not be prime because we know from above that even numbers can be divided by 2, so it should have more than those 2 factors of itself and 1. A few other examples will be 3, 11, and 17. And while there are more prime numbers than these 4, these are just a few examples. Our fourth number classification is going to be the opposite of our prime numbers, called our composites, and these will be numbers that have more than 2 factors. 4 will be an example of that. Its factors are 1, 2, and 4. 1 times 4 will equal 4, 2 times 2 will equal 4. But because it has more factors than itself and 1, it will be considered composite. Even numbers will not only make up our composites. There will be some odd numbers that are also composite numbers. For example, the number 15 has 1 as a factor, 3 as a factor, 5 as a factor, and 15. Composite numbers are made up of both evens and odds. And our last number classification are called our opposite numbers. We saw that a bit when we were talking about integers, but just to get a little bit more into it, these will be numbers that are equal distance from 0 on the number line, and that is what is making them opposite. For example, if we have 0 in the middle, I can have 1 here and -1 here. They are both one space away from 0, and that is what is making them opposite. As we kind of do this in real time, if we have a positive number, then its opposite will be that negative value. Now let's do one more guided practice. The first thing we'll do is circle numbers that are even and underline numbers that are odd. The second thing will be to circle numbers that are prime and underline composites. And the third thing will be to write the opposite numbers for the given numbers. Take some time, pause the video if you need to, and on your guided notes page, complete all 3. Amazing, so now let's look at the answers for the first one. Circling numbers that are even will be -58, 0, and that's all. Numbers that are odd will be 203, -90,651, and 17. Our next one, we had to circle numbers that are prime and underline numbers that were composite. 13 will be an example of a prime, and 2 will be an example of a prime number. Again, 2 is our only even prime number. For our composites, we have 49. 49 was an example of our perfect square, so we know it has more than itself in 1. It will also have 7. Our next composite number will be 60 because 60 is even and it's bigger than 2. 1 does not get anything because 1 is not considered prime. The third thing we were asked to do is to write the opposite numbers for the given number. The opposite of -7 will be +7, -15, -9, +23, and +82. For our positives, we don't have to include the plus sign. If we don't include any sign, it will be assumed that the value is positive. Thank you so much for taking the time to learn with us. Keep up the great effort. If you're looking for some more practice problems, there'll be a few problem sets in the link in the description. Thank you so much, and we hope to see you next time. Bye!